And this is part of my education campaign to the universe. I want to convince the scientists of the universe that an operating principle that unites what the theorists are able to tell us about many body quantum dynamics and what the experimentalists are able to realize in the lab. An organizing principle is transient impulsive excitation. And if you want to know what transient impulsive excitation is, you know that bell that rings at the end of coffee break is an example of transient impulsive excitation. I can guarantee that that hammer is not a tuned instrument, but
this is a Swiss cowbell.
But the bell has resonant frequencies which can be excited because that hammer is so broadband. And that's the impulse. So now you get the idea. Now you can just drink your coffee and doze for the rest of the lecture. This was working before. I think it was working before and then I undid it. All right. Now, laser interactions with electrons produce a hierarchy of motion in molecules, lots of different timescales. That's good, because us experimentalists maybe only have access to some of those timescales, and then we can pretend that the timescales we have access to are precisely the timescales we needed by judicious choice of physical problem to study. Now you know how that works. So, molecules undergo free rotation in space, which can be picoseconds and more. Actually, for hydrogen, which you might think would rotate pretty fast, its slowest quantum constant of rotation is on the order of a picosecond, and then bigger things are even slower. So in this attosecond conference, rotation is imponderably slow, but we can still study that. The molecules also bend and stretch, and the timescale for that is tens to hundreds of femtoseconds. The timescale for the binding electron motion in small timescales, that's determined by particle in a box. It's determined by the fact that the Coulomb binding potential is something that produces a bound state that's always on the order of an angstrom. You know, this is the reason why, you know, all atoms are to first approximation the same size, because that last electron always sees only a simply charged object that it has to be bound to. And so it's always, the box is always the same size, about an angstrom. And so you stick these things together, and the binding motion is determined by that angstrom size and the Rydberg binding energy to be on the order of a femtosecond, a couple femtoseconds or shorter. And then finally, we get to the attoseconds part of this. Those inner electrons can be bound by hundreds of volts or kilovolts, and they are confined. They are the ones that are confined to by inner charges of the nuclei that are much higher than a single charge. And so that's much smaller than an angstrom, and so that implies attosecond motion. So we get this whole time scale hierarchy here. And it's all, of course, subject to the ultimate barrier that we have to deal with in real-world physics, which is that the speed of light is 3 angstroms per attosecond. So will we do zeptosecond atomic physics? I think no. We might do zeptosecond nuclear physics, because nuclei are small enough, but not atomic physics. This attosecond timescale is a playground we can play in for a long time. Okay, so we want to launch and probe this motion. Launch and probe, pump and probe, that's our method. And our guidebook, the rule book, is a single line here in non-relativistic quantum mechanics, Schrödinger's equation, of course, first order differential equation in time. So all the dynamics is there. And our part as experimentalists is to add an extra piece to that Hamiltonian. Laser, particle beam, whatever it is. So now we have an explicitly time-dependent part, whereas the ordinary Hamiltonian object that we're dealing with will typically, the Hamiltonian will not be time dependent. All the dynamics comes from this equation, not from the time dependence of the natural Hamiltonian. That will not be true once we turn on our laser, then we have an explicit time dependence. So what are we going to do with that? Well, that interaction Hamiltonian is, of course, the way we view the world. So we can think of it as our shutter speed. Shutter speed for making molecular movies, single frame. Also as the starter pistol for initiating dynamics. And in the impulse limit, the shutter speed has to be fast compared to the natural motion. So I've just described the hierarchy of natural motion. And that means that the time that we're talking about has to be less than something that's inversely proportional to the spectral energy splittings, simply by Heisenberg, you might say. And also, so that's short, that's the impulse limit. In addition to the impulse limit, we also might have other technical things that we want to accomplish that will cause us to be interested not only in this time, but also in the relative size of h int compared to h0, the relative size. The applied field has to be strong enough to alter the natural dynamics, or else there's nothing that we can see in the lab. So here's our sources. We've talked about them throughout the week. First of all, there's optical lasers, and I'll concentrate on titanium sapphire because it's the most commonly used for this kind of thing for completely boring technical reasons. You know, if we had this winter school in 1989 or 1990, this would have been a dye laser, but by 1992 it was a TISAF laser, has been that way for the succeeding whatever it is, quarter century. So that's our visible laser, but of course it's something that through nonlinear optics and atomic physics we've been able to convert into high harmonics. And look, that's a much higher bandwidth and therefore capable of much shorter pulses. That gets us into the out-of-second regime. And now we have X-ray free electron lasers, which are tunable over orders of magnitude centered on X-ray wavelengths, which means that we have all the bandwidth we could ever want. All we need to do is learn how to control it in order to use it. Okay, so two-dimensional plot here. Time versus intensity. As we go up in intensity, we increase the size of this guy. As we change the time scale, we go from being able to look at femtosecond down to attosecond processes. So let me start with something that is about 15 years or more old, and that is just to demystify something. I mean, people think, oh, it's so exotic. Well, you know, the wonderful thing about Coulomb systems is that they have any energy splitting you want. You just have to find the right pair of principal quantum numbers. You could be doing microwave ultrafast wave packet spectroscopy if you wanted, and there are people who have built their careers on that as well. Just as an example, something that we did a while back, weak field now, not strong field, is excite a superposition state of Rydberg wave packets just to get into this regime, delta t less than 1 over the energy splitting, and then you make a superposition and it can evolve, and you can do a pump probe kind of experiment to map the evolution of the wave packet in space, and it looks like this. The nucleus is here. This is the outer turning point of the outer Rydberg orbital that we studied. These are all p orbitals, so they all look like these jelly donuts in three-dimensional space, and if I plot the radial coordinate, you see as a function of time, it oscillates back and forth just because of the natural evolution, free evolution of these timescales. So that's a way that to initiate and observe dynamics. This is very boring by today's standard, but it actually isn't too different from everything that we're doing. It's just that we've now moved these down into the regime where we can look at bonds breaking and being made in molecules and that sort of thing, and maybe learn more than here. Here we learn about the dispersion of Kepler orbits. Okay, not that big a deal. Okay, that was weak field. Now let me talk about just sort of the way to think about turning up the field strength so that you can begin to interact a little bit more strongly with your system. and still in this impulsive regime. So by impulsive, I just mean that timescale restriction. Timescale short compared to the energy splitting. That didn't have anything to do with the field strength. The cowbell could be tapped just very lightly, and it would still work. Right? So let's turn it up a little bit. We'll go now into this Kramers-Heisenberg regime. Not yet super strong field, non-perturbative science. Still perturbation theory works, but second order, so that you get intensity-dependent effects. Okay, everybody should know basically about second order time-dependent perturbation theory, and the interaction with material systems is encapsulated in something called the Kramers-Heisenberg formula, and I'm sure that you've seen it in some context before, but particularly the version of Kramers-Heisenberg that I care about is not two-photon absorption, but rather one photon in, one photon out, photon-photon scattering. That's called Raman excitation. And I want to look at this now in this impulse limit. Okay, here's just a standard formula. I cut and pasted it out of, I don't know, whatever paper I did, but it has all of the features you expect from Kramers-Heisenberg, a two-photon process. Here's the Feynman graph. Initial state comes in, interacts with the photon. Some intermediate state, which is just virtual because it's a single second order process here. Photon goes out, and now I have a final state. Here's the map. Single state, photon in, photon out. I'm in this impulsive limit, so these photons have bandwidth, and now I can interact coherently with any of these states. Okay? Here's how it depends. It depends on how many photons you have per mode in your field. It depends on the dipole couplings here and here. Here they are. It depends on other things having to do with the polarization and the frequencies of the field. To go to the impulse limit here, I have to convert this n number of photons per mode into in a mode into intensity, and then convert that intensity into the total fluence in my pulse. So the total transition probability then is just the integral over all of the energies in my pulse of the fluence, and so it naturally goes like the intensity squared. And that's what you expect. It's a two-photon process. It better go like the intensity squared. Okay, simple example of doing this. On the slowest time scale I talked about, just rotation. Nothing out a second yet. Okay? So I have a short pulse. And how can I think of this short pulse in classical electromagnetic field space? Well, like, usually you write it out, E of t. Okay? And then if I ask the question, what's the frequency content of that pulse, you'll say, well, it's left to the reader. You Fourier transform this in your head. But there are other ways of describing completely the classical electromagnetic field that are a little bit more useful than just E of t. And one of those ways is, of course, the Fourier transform of E of t. Well, that has its own problems. I could give you the spectrum, and for a Gaussian pulse, that would be a nice Gaussian spectrum, right? Also, the spectrum is also Gaussian. You say, okay, Gaussian spectrum, and phase is flat. Fourier transforms, I'll have to tell you the phase, right? Phase is flat, and you could say, what is the time dependence of this pulse? You say, well, I leave that to the reader. You inverse Fourier transform this guy. Also a little bit less than completely obvious. But, as you know, as good theorists always know, this is very important for experimentalists too, but often they don't know it. Okay? What you should always do when you're about to solve a problem is find the appropriate basis for your spectrum. And I presented you E of t, E of omega. Neither one's pretty good. We have to kind of, time, frequency, let's go in between, okay? So one way to go in between is by re-expressing the field through a Wigner distribution. It's now, instead of a complex function of frequency, it's now a real function of two variables, time and frequency. And it's completely derivable from either of those other two ways of completely describing the classical field. And you can see it kind of looks like this correlation here. Here it looks like on a two-dimensional plot, frequency and time. The line outs, if you integrate over all the frequencies, is the intensity versus time, and the line out, if you integrate over time, is the intensity versus frequency. And if I have a short transform limited pulse, it just looks like a dot, a bullseye, a Gaussian hill on that space. Now I'm going to use that bandwidth to do Raman excitation of some system rotationally. Okay, so that means I'm going to kick it. Now you know that's what I mean by kick. So kick now becomes one of these terms of art, like red, or blue, or doubling. Right? All these words that we use that people who aren't in our field will completely misunderstand what we're talking about. But we understand. We understand. Okay, so we'll kick this system, impulsively excited, and take a look at the expectation value of the alignment as a function of time, and it goes through periodic motions. We're making rotational wave packets. There are periods of angular focusing where the molecules all align. Actually, that happens very early. And then because these levels have a harmonic separation, the separation just increases linearly with the same linear constant every level. This is a polynomial expansion, which means that there will be revivals. That's what you need for revivals, for real revivals. Now, Coulomb systems don't have that because their spacing isn't describable by a polynomial series. It goes like 1 over energy squared. So you only get approximate revivals with Coulomb. Here you get real, truly, really revivals, assuming it's truly a rigid rotor. Okay. So there it looks. Okay. And you can now begin to do impulsive physics with this system. Let me just do the simplest thing, which is look at how I can optimize the amount of alignment. This turns out to be just a practical thing. I happen to be in a business where I much prefer to work in the molecular frame all the time. So maybe I could create the molecular frame through impulsive excitation. That's a pretty cool way to do it. But then I have to get really, really good alignment. That means I want to optimize the expectation value of cosine squared theta in the lab. All the molecules aligned in the room. Okay? Well, the first idea about how to do that is to make sure that my gas is as cold as possible so that I have only a few of these rotational states initially excited. That will help. You can see it really does help. Here's a plot of what cosine squared theta should be as a function of different temperatures of gas for different kick strengths. This is a log scale of kick strength. So you can see you kick it harder. If it's colder, it works better. You can even get alignments up in 0.9 range. You run into a problem when the dimensionless kick strength gets to about 3 dimensionless units. That is a really strong kick. That sort of corresponds to Pierre, instead of just using the clapper on that bell, if he were to take a sledgehammer to the bell, okay, it would stop working, and it would stop working permanently, you know. You wouldn't be able to use it. So the same thing happens with molecule. If you kick it too hard, it dissociates, and then game over. So you can only kick it so hard, that means you have to make it very cold. Okay, let's do a little impulse physics here. What happens if we kick it a second time on one of these revivals? Here's the first revival at 8 picoseconds. That's a full revival. There is 8 picoseconds. Here's the delay scale. Kick it again, 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 kick it again. I can do that simply by creating a different electric field than this one. Here's an electric field that consists of 8 Gaussian pulses with the right spacing, about 8 picoseconds. Here's what the visionary distribution looks like, the complete description now of this field, in case you care. Okay? And if you keep each individual kick below this magic line, of course you can overcome that. You can see it gets more and more aligned. You can overcome this death by kicking too hard and get much greater alignment, even for room temperature samples. You can get alignment that is comparable to what you would have to get with very cold samples. So there's just an example. Okay, I wouldn't say this is a momentous moment in human history, but it's a great instruction about the utility of this impulse idea, impulse approximation, in getting different kinds of physics done in the lab. Okay. So of course, naturally, we did this. So let me just wax you know, go off on telling you how wonderful it is just for a moment. Again, expectation value of the alignment. And we began to try to do different kinds of physics with multiple kicks. Every kick has to be impulsive or none of this works. So this is really the impulse limit physics. Okay? One of the things you can do is change the relative spacing of these kicks by introducing disorder. Now you might think that's not going to be very interesting, because if I introduce disorder, I'm going to mess up this beautiful resonant kick stronger, the kicks align more and more and more. And surprisingly, at least at first, surprisingly, that's not true. Let's take the case of no disorder. The kicks are absolutely uniformly spaced, but they're slightly off the resonance. They're not exactly on the exact revival. Well, what happens is what you might expect. There's a couple of wiggles, but pretty soon you get to a saturation because your kicks are now no longer doing any positive benefit to the ensemble that was previously kicked. So you get some saturation, and you might expect that the position of the saturation point depends on how close you are to the resonance. Now, all you need to do is introduce disorder, and it will always get better. Periodic disorder, these are simulations. Periodic disorder gets you a little bit better. Aperiodic disorder gets you even a little bit better. Full disorder, just throw in a random number generator on the kicks, and actually that does the best. And if you compare this does the best with what you would do if you went back and now let's go exactly to the resonance and just keep increasing the number of kicks, you do better with full disorder. Here's perfect resonance. You get these nice little oscillations. And then it flattens out at a particular kick strength and at a particular amount of alignment, and disorder does better. So it's interesting. That's actually, it's an analog mathematically to the same physics that's responsible for Anderson localization. It's actually a disorder-induced localization phenomenon, in this case localization in angle space, introduced by disorder in a completely coherent system, non-dissipated coherent system. This is just what Anderson localization is about.
I have a question.
Yes?
For the last one, the kick on revival, if you made more kicks, would it go up again?
No.
It doesn't?
Would it start oscillating with higher amplitude? Yes.
Okay.
I mean,
Because it looks like it would start to go up again.
Yeah, it does. That is, as this would, yeah,
Right.
that's right, it will. Okay, the experiment, okay, we're experimentalists. We had these simulations. Our collaborators at Weizmann, Johannes Floss and Ilya Abergut did simulations. We did experiments, and it matched quite well. Now, what about this oscillation? What's this? These are actually Bloch oscillations. I mean, it's just the same. It's one-dimensional Bloch lattice in angular momentum now. And so all of this physics that you know about, that comes out of thinking about periodic systems, applies to this temporally periodic system. It's just the time is the periodicity you're worried about. Okay, that was kind of cool. Let's now get to more molecular physics and atomic physics that we care about. How many different ways can we think of to create this impulse condition? So, for example, there's been a lot of talk, particularly by me in my first lecture, about strong field ionization. Not only by me. Of course, it's essential for harmonic generation and for the generation of attosecond pulses. So let's just think about that ionization itself. Is tunnel ionization another form of sudden ionization for sure? I mean, the model is ionization happens at some threshold condition for the electric field, which is oscillating periodically, so you get to that threshold and boom, everything happens. Sounds impulsive, kind of, right? So it's certainly sudden, and in this definition that I made of what an impulse is, that is the time scale of the interaction is shorter than 1 over the energy splitting of the energies involved, right? It's impulsive. And in fact, here's a little cartoon that makes that even more highly motivated. And that is that this is diatomic molecule. Think of this as nitrogen. This one that often gets used. And let's say that it's now perpendicular to our strong laser polarization. And so the tunneling will happen through some little saddle point here. Okay? And now let's project this location of this saddle point on the spectrum of states, and we'll see that it actually projects onto more than one state. It's not just the highest occupied orbital that has some overlap with that position in space. The other orbitals do too. If I can think of ionization as just allowing stuff to leak out through that hole, then what leaks out should not just simply be the lowest or the highest occupied orbital, but some of the inner orbitals, which are more deeply bound, but are also located here, should also participate. Okay, so there's a prediction based on this idea of impulse. That participation should be coherent so long as that tunnel ionization was fast compared to the energy splitting. This is where the energy splitting compared to the time of the interaction comes up. Okay, is that clear? Yes?
Could you say that again?
I have an energy splitting between, natural energy splitting between different orbitals in my system. Okay? I have a highest orbital, I have a next highest orbital. There's electrons in these orbitals. It's a closed shell system, so it's actually got multiple electrons in these orbitals, right? I'm now going to suddenly, or at least sudden in the context of what we define as an impulse, suddenly tip the potential. Water starts to slosh out of the bathtub. Electrons start to slosh out of the potential. Okay? Where did they come from? Which orbital will feel the loss of an electron? That's the question. And the answer I'm proposing is it's just an impulse limit kind of a thing. If the time scale for that sudden tunneling is fast compared to the energy splitting between these levels, and if the other conditions, like the position of the tunnel is in the right place where those orbitals exist, then we should naturally pull out from more than the highest occupied orbital. Okay? Okay, well, high harmonics experiment. This is the first high harmonics data I've shown, but everybody can play that game. You can go back to your own labs or your laboratory friends and say, hey, you should do some high harmonic stuff. It's easy, it's fun. And so here's some high harmonic spectrum from nitrogen. Aligned nitrogen. Always take the stuff early in your talk and use it for the stuff later in your talk, right? This is aligned nitrogen. You know how we align it now. And here is the highest occupied orbital in a nitrogen that has its axis oriented this way. Here's the next orbital. And what I do is I change the angle of my strong field ionization with respect to the alignment, which now I know how to do. Okay? And I see how the spectrum changes. When you get out here to 90, you kind of get a new little piece of high harmonic spectrum coming out. Okay? And what we were able to show in a number of papers was that this actually is caused, and has now been confirmed by other people, so it's pretty much accepted. It went from, we don't believe it, to, oh yeah, that's boring, which is a wonderful thing for experimental research. You get to that limit, and you've won. So this is in these, oh, that's boring stage now. Yeah, sure, when you're out here, you get this extra piece because there is harmonic generation caused by tunnel ionization from this orbital, in addition to this orbital, for exactly that reason that we discussed. So that's happening, okay? Everything I just said, I'm just repeating on this slide. Sorry about that. High harmonic spectra suggest coherent tunneling from multiple orbitals, leading to attosecond beats. And the experimental evidence is, yeah, you see, that happens. So, even take it further, I showed this slide before, didn't really explain very much about it. It's another high harmonic spectrum, now from a much more complicated molecule, sulfur dioxide. A triatomic non-linear, it's a bent molecule. And you try to kick that and it tumbles, but in a coherent way. It doesn't align, unfortunately, it's an asymmetric top. But it does undergo coherent rotational wave packet evolution, which you can track and deduce from that evolution simply by looking at where these peaks and dips are in the harmonic spectrum as a function of time delay since when you kicked in. You can deduce again which orbitals are participating in the SO2 harmonic generation, and no surprise by this time, of course it's not the highest occupied molecular orbital. It's any orbital that's hanging out there when it can participate in harmonics, and in fact there's a Nature Communications that gives a little bit more details about this particular case. Okay, so we learned that that process of tunneling out that leads to harmonic generation can itself be thought of as an impulse. Okay, let's do a few more things with that idea. Okay. I'll come back to the electronic orbitals in a minute. Right now, let's concentrate on something that's a little easier. That is the vibrational and bending motion. Here's water. Water looks like this. This is the highest occupied molecular orbital on water, sits on either side of the plane of the bent water. I suppose some of you already knew that because it's certainly one of the most well-studied and well-understood systems in molecular orbit theory. And the HOMO -1, the next most highly bound, most weakly bound occupied orbital, that is the one that's next down, it looks like this. It's actually in the plane of the water, and it's the electron that provides the glue that shields these protons from each other to allow the water to be bent. Otherwise, it would be a linear molecule because the protons want to repel each other. So why shouldn't it be linear? And the answer is HOMO -1 forces it to not be linear, forces it to be bent. Okay, that's kind of interesting because it means that we already know we can, depending on the orientation of the water, either remove this electron in high harmonic generation or remove this one. But if we remove this one, actually, of course, there are two, it's closed shell. But if we remove this one of those, the water's going to want to unbend. Actually, that's trivial, that's well known. That's this potential energy curve where the HOMO -1 is the orbital you remove, and this is the bond angle. And 180 degrees, when a bond angle is 180 degrees, the molecule's straight, right? Here's where it likes to live when it's in the ground state of the neutral, and here's where it would like to live if you remove the HOMO -1. You see, that's the minimum. Okay? So if we can remove this one, the molecules will start unbending. Okay, when they unbend, here's a little cartoon. When they unbend, they're now in a different state when the electron comes back to make high harmonic radiation. So we can see the impulsive aspect with respect to the bending motion simply by looking at the high harmonic spectrum for water as a function of different parts of the spectrum. This should affect the blue part of the spectrum much more than the red, because the blue part is the longer trajectories, which are returning much later. Okay. Well, okay, the poor man's experimental approach to testing that is to try this for H2O versus D2O, because they have exactly the same electronic structure, but the protons are twice as heavy, right? To go from protons to deuterons, so it unbends slower. And to look at the ratio of the harmonics on the red and the blue part of the spectrum for D2O versus H2O, and it's a huge effect. It's a 15% effect, simply because it's so probable to ionize this HOMO -1 orbital. And then you get into this impulsive excitation of bending. Okay. All right, so we talked about exciting superposition states of vibrations just by tunnel ionization. Of course, we already know that we can excite superposition states of bending or vibration with short laser pulses, but now you have this new insight because of this the snake oil that I'm attempting to sell today. If that pulse is short, then it has coherent bandwidth, then it is impulsive with respect to levels that are within that bandwidth, and those are the vibrational emotional levels of a molecule. Now, this can actually be controlled even just by the Frank-Condon integrals. That is, if I have a short enough laser pulse, I'll excite a lot of different bandwidth up here just because of the Frank-Condon integrals, and then my system will start to move. Now, this particular picture is for a whole experimental program. I'm not going to explain it based on the physics of the particular program, which involve, conical intersections, all kinds of nice stuff. It would be if they allowed us to give 4 lectures, I might talk about that. But now just think about the motion. It's just the motion. I'm exciting coherent motion because of this of this impulsive limit, and I can now probe it. And here, the idea is I'm going to probe it with X-rays. Okay? So, how does this work? Well, this molecule is very complicated. It's called thymine. It's a DNA base. It's got a ring. It's got nitrogens. It's got oxygens in addition to the carbons and hydrogens. And when it gets excited, one of its bonding orbitals, like these guys here that are holding the ring together, one of those pi orbitals gets excited to an antibonding state, like a pi star state, where now that place where the molecules were being held together is being pushed apart. That's the excitation. That's what causes the molecule to move. Here you see it moving because of it. Okay? Because we can do this impulsive excitation, we can ask what's the overall timescale for the motion, which states are populated, and how does the geometry change. And our method to answer some of these questions is to probe it by X-rays, which will concentrate their effect right over atoms, individual inner orbitals in atoms. So we chose an oxygen atom, we excite this moving state, and then we probe it by removing an oxygen inner electron. And depending on where the molecule has moved to, that leads to an Auger decay that will have its energy shift dramatically. So it's like an amplifier. So I have a little bit of motion, it's an angstrom motion. How can I see that? I can see that by sending in another pulse in an impulsive limit that removes an inner electron, suddenly changes the charge over here, not anywhere else in the molecule. And then the Auger relaxation will depend very, very strongly on where the other electrons are with respect to that place. And since the molecule is moving, that's what's changing fast. And I should be able to see that in my spectrum. And you can. This is the electron kinetic energy from the Auger process versus the delay between the excitation and the X-rays. And you see the Auger spectrum suddenly shift. Okay? Blue means less, red means more. So there are more Auger electrons coming out at a high energy, and then suddenly they come out to low energy. And you can analyze that, where that's coming from. Here's the oxygen atom. This is the oxygen atom that where everything must be happening. It means that the electron cloud is moving with respect to this oxygen atom. And you can relate that directly to the geometrical move of the molecule. So, rather than give a whole lecture on this, I'm just giving you the snapshot. The bottom line here is that any kind of molecular or electronic or coupled molecular electronic motion is now open to you to view directly with a probe because we got into this limit. All we did compared to previous experiments at synchrotrons was have the pulses be short enough to be in the impulsive limit and look in the time domain to see the motion directly. You can also do this with 2 X-rays. We can induce the same kind of coherent motion with an X-ray by, say, take a simple molecule like acetylene. Acetylene is HCCH. Acetylene is a linear molecule. It's kind of interesting. If I do HOH, that's water, molecule bent. HCCH, molecule straight. Okay? What a difference that central core makes. It's really, really critical. So that's a straight molecule. It doesn't stay straight once you start removing electrons. And so we do a 2 X-ray pulse experiment. They're both very short. One comes in and does whatever it does. In fact, what it does is it removes one of these carbon electrons. Here's a picture of Gozella. Removes one. And then later, a probe delay comes in and it removes another. Now, I have 2 electrons that have been photoionized. I have 2 relaxation events in between, 2 Auger events, and I have a 4 times ionized molecule. I have 4 atoms in this molecule. It can fly apart a la Paul Corcom's Coulomb explosion. I can then look at the direction of the momentum and the energy of the particles and reconstruct the geometry. And again, the bottom line is, by being in this impulsive limit, I get to look at the geometry of the molecule. In this particular case, the thing that we cared about was that when you remove a couple of electrons, the molecule really wants to have one of these protons, in this case it's a deuteron because we wanted to slow it down, one of these singly charged atoms move over to the other side to form this isomer of acetylene. It's the smallest molecule that can isomerize, has to have 4 atoms. And essentially OCS, OSC. Anyway, so this one isomerizes. And you can see that. You can see it happen here as a function of time delay over a few femtoseconds. This looks like lousy data, and it is. But it demonstrates the principle that you can see isomerization of the pulses are short enough. Okay. So let's now get into the regime of X-ray ionization. When X-rays ionize something, as you heard from Linda, there's a very strong tendency for the ionization to be an inner shell. Right? Just a cross-section thing. There are way more electrons up here, way fewer here, doesn't matter. The cross-section is so much bigger here, orders of magnitude bigger. So you tend to ionize. 9 electrons will come out this way before 1 comes out this way, something like neon. So it's a pretty good bet that you ionize a core electron. That means all of the other electrons think that the atomic number of one of the atoms that is holding them together just went up by 1. That's basically what they'll think. And they'll respond really fast. Okay? So you can see this response in calculations. And this is a simple calculation that was done by the Cedarbaum group for a number of different atoms and molecules, where their idea was, let us make I like this group because they really get the impulsive idea. They said, let's make something, the limiting impulse that we can possibly apply to it. The experimentalists can't even touch this, it's so impulsive. We will simply erase one of the electrons at t equals 0. And then let the system evolve. Okay, not only is it a clever idea, but it's also like really easy, right? It's an easy thing for them to do. And what they observe is that no matter what the system, if they look later and see whether that hole they created has survived, it doesn't survive. I mean, it does survive for a long time, but it starts to fill in right away. In fact, it starts to fill in as little as 25 attoseconds. For any of these cases, this is krypton. They didn't even go to 1s. They went to the krypton 2p. Here's the 1 pi u CO2 state and the 3 pi state in this methyl acetamide. And it's just a kind of a universal thing. So you want to do out of science, impulsive X-rays seem like a good bet. Okay. So we have to sneak up on this problem because we don't have 50 attosecond kilovolt or even 100 volt. Well, maybe we do have 50 attosecond. But it's sort of at the limit of what we can do. So one can look at this in various ways. One is that let me just do this in a molecule where I remove this, and then the Auger happens, and I'm left in after a couple of femtoseconds in a doubly excited state. Doubly excited states of nitrogen are interesting. Some of them are kind of almost bound. And a lot of them have very significant quasi-vibrational levels, quasi-band vibrational levels. A lot of them do. This one does. This one does. These are all of these energy levels as a function of internuclear separation. And the nitrogen dication, they have, of course, the diatomic molecular symmetries. Okay? And we can ask the question first, was it really impulsive in the sense that we made all of these states? And the answer to that one, that's a trivial one. The answer to that one is absolutely it's true. And then ask the question, if we make them, can we get coherent vibrational motion? Because obviously it must have been impulsive with respect to these vibrational levels. And the answer there is, in order to see that, we would need to have very good time resolution in our pump probe experiments, which we don't yet have, but you know that's probably there as well. We have actually tried to do this by probing with an 800 nanometer laser, and it's kind of inconclusive because the pump probe jitter has to be minimized to reveal it. But we're sneaking up on that, okay? Of course, the real idea of going to X-rays would be to look at something that happens very fast, like charge migration. Charge migration, as we saw, is supposed to occur in attoseconds. And you know, would there really be a science payoff? At some point, you have to ask yourself, if your field is attosecond science, at some point you have to ask yourself, are you really just messing around because the technology is now advanced to where you can make these things, but actually it's hard to learn something new? I ask myself this question. So let me make a pitch that you can learn something new in the impulse limit. We know that charge migration initiates all of charge transfer chemistry. That is, first an electron moves, then other stuff happens. Okay? And an electron, and the first thing that happens in charge migration is that all the other electrons, you know, to the extent that I can think of this as the electrons are distinguishable, of course they're not, but I have this fiction that they are, and I can move one, or move one, and then the other ones all relax around. Okay? There is a classical theory of electron response where it's as simple as it can possibly be. It's called Marcus theory. There's even a Nobel Prize for it. And that is that you can think of all of the electrons as living where they live because they're in some generalized sense at the bottom of some parabolic potential well. And if I change anything about this molecule, like photoexcited, for example, then I displace that potential well to some different potential well. And the molecule is no longer in the bottom of a potential well. It's now way up high in a potential well, and it's got to relax. Oh, this is such a simple idea, it can't be wrong. Right? And the opportunity and challenge, particularly in theory, for this attosecond charge migration stuff is that this is the only bar you have to beat. This is actually considered the current. This is the way one should think about charge migration. So let's do a better job, and that'll be great. So I think there is a strong motivation to be able to work on this problem. So we would like to work on this problem as well from the experimental side. So we have to construct these sets of very, very short pulses to interrogate our system. And the rule, again, is that each one of these has to be impulsive with respect to the energy scale that we care about. And then we can do multidimensional spectroscopy. So we can create through, for example, if one of these does core excitation, it can create a localized electron disturbance, and then there'll be some relaxation, some non-local electron transport, which we can then probe. Okay? Now, a refinement of this idea, or I should say a subset of all of the ways you can do this, is to have those impulses actually not just suddenly change the system, but change the system in a strong field way, that is, undergo a Raman redistribution. So this solves a very important problem, a conceptual problem, in photoexcitation physics. Is if I'm trying to take a system from its ground state and put it into an excited state, that, if I want to do that resonantly, then I'm kind of stuck with that resonant frequency. But if I'm trying to do it impulsively, then that resonant frequency is got to be in the middle of the bandwidth of my pulse, which is sort of impossible. That means you have 100% bandwidth pulse. If you do it using strong fields in a Raman way, then the central frequency of your excitation can be way up here, much higher frequency, and it's easy for it to have enough bandwidth to cover all of these states. So Raman then becomes really necessary to get into this impulsive limit. That actually also has an advantage, because since this is a 2-photon process, whereas all of the background processes like direct ionization are 1-photon processes, I should be able to go to high enough intensity to get the 2-photon process to actually dominate. So we did a little, this is the thinking we go through. So we did a little calculation for sodium to find out where this would happen in inner shell ionization, inner shell excitation using Raman and sodium. And there's certainly regimes where you're at 10 to the 15, 10 to the 16 watts per square centimeter squared. Should be accessible. We should be able to get to those intensities if we choose the right system. So notionally, it's not a crazy idea to go in this direction. So here is a test case. So this is an excitation in the sodium atom. And the sodium has some resonances way up in the continuum at high harmonic type frequencies. This is photon energy in EV, 32 to 40. Okay, and we can excite sodium to double it to inner shell excited states, embedded in the continuum in this range from 36 to 38, and then we can drive the 3s electron, the one that used to be the outer electron before the excitation, back down to fill the hole. That's the Raman process. So the Raman process is we can go from 2p6 3s, that's sodium, to 2p5 3s ns. The 3s is still there. And then take the 3s electron and send it back down. That's the Raman process. You end up with a neutral that is in an excited state, and the time it took you to do it is short compared to the entire width of your sodium spectrum. So that's an impulsive excitation. If you want to think of it, that's the sort of technical detail behind kicking a sodium atom so hard that it becomes an excited sodium atom, rather than become ionized. It's a swift kick that is required, right? If you kick it slow, with that much momentum transfer, you'll just ionize it. If you kick it fast, it'll stay neutral, but be excited. You have to kick it fast compared to the natural dynamics of the 3s electron. What's that dynamics? It's given by this energy splitting. Okay. That's the idea. That's all there is. Clever idea. Actually, if you do the calculation, you can get some really interesting looking stuff. This is for a Fourier transform pulse that I'm going to use for Raman that's a few femtoseconds long. 1 femtosecond, 3 femtoseconds, or 5 femtoseconds are these 3 dotted lines. Okay? And you see that if I ionize my system with a 5 femtosecond pulse, let's start there. That's the blue dotted line. So I'm going to tune a 5 femtosecond pulse all the way across this band. It's VUV, high harmonics. I could do this. Anybody could do this with high harmonics. Tune across this band. See, you don't get very much ionization. You get some. But then you get to these resonances and you get a lot more ionization. If I make the pulse only 3 femtoseconds long, I get ionization. It's not getting smeared out by the coherent bandwidth of my 3 femtosecond pulse. 1 femtosecond long, it's just a big blob with a bit of an enhancement because of those autoionizing states. That's the ionization rate in a real calculation. What about the Raman rate, the rate for Raman distribution, the really fast kick? Well, start with the 5 femtosecond pulse. 5 femtosecond Raman, that's the solid blue line. Okay? It's down here 12 orders of magnitude down from the top here. So with a 5 femtosecond pulse, it's so long, you never leave the system excited. You're kicking it too slow. It's like taking the cowbell and putting it into a crusher instead of hitting it. Okay? You're kicking it too slow. It won't ring, right? Okay. Make it 3 femtoseconds long, and things get better by 6 orders of magnitude. Big deal. It's still way below what you need. But suddenly, at 1 femtosecond, this is what Raman does. Raman actually beats by an order of magnitude ionization. That's all. That's all there is to this. It's just kicking something fast enough. You can get the visual excitation happen. So we propose that this is a good thing to do. Okay, here's what we need. 5 microjoule, transform linear pulses, 35 eV, 1 femtosecond full width half max. And here is the Moore chart, or the Moore's law chart, on what people have been able to make with high harmonics. Midori-Kawa is getting 500 nanosecond pulses. That would be good. At around a microjoule, we're getting there. We're getting there. We're getting into this regime. Probably in the next few years, we can actually do these kinds of experiments. Which means it's perfect time, if you are interested at all in this impulsive stuff, to start calculating what would be interesting to look at. So we're getting into this regime. The first paper on this, Shungu Mayabi is the theorist. He was actually from our PULSE Institute, who worked on this with me, but you know, the whole landscape is wide open for this. Can we do this with free electron lasers? Now we're getting down into the hundreds of eV or kilovolts. And the answer is yes, you can. Nina Roeringer actually proposed it already, kind of, although she didn't have this impulsive idea in her mind. She was thinking, oh yeah, Raman's a good thing. She's right, it's a good thing. But impulsive Raman, even a better thing, she wasn't quite there. Her idea was 2-color Raman should work. Excite and de-excite. What happens if you go to one pulse that has several eV of coherent bandwidth? This is this idea that we call TIGER, because you have to have an acronym in anything with X-rays. Transient impulsive giant electronic Ramans. Tell all your friends. Great. Anyway, so here's what happens if we have 1 femtosecond pulses in this region of around nitrogen Raman excitation with X-rays. And the same calculation. At what point does ionization beat? At what point is ionization beat by Raman? What point is Raman better than ionization as you go up in intensity? Now we have to get up to around 10 to the 18 watts per square centimeter. Sounds horrendous, but you just heard how, from Linda, how X-ray lasers can be focused to 10 to the 22. So this is, again, within the regime, if we can get the bandwidth enough. And so we have real schemes for this. I'll skip over the scheme and show you something about the pulses. Okay, can we make attosecond X-ray free electron laser pulses with that kind of bandwidth? And the answer is sure. The answer is we're probably already doing it, but we don't have good ways to control it. Here's a scheme, for example, that back in 2009, Yuan Tao Ding published about how with a small amount of playing around with the electron beam before it enters the undulator, you can make single spike radiation that's hundreds of attoseconds in width, with powers of still in the gigawatt range, so we're still able to focus it. And then this is what I like the best. This is something that just came out from Jerome Huang's group. He points out that at free electron lasers, if you can really do the micro-bunching. How many people remember all the way back to my second lecture what micro-bunching is? Remember micro-bunching? It's kind of a cool idea. Jerome realized that micro-bunching is so tight that even though these electrons are relativistic, it's so tight, you actually get some space charge chirping just because of the micro-bunching, which hadn't previously been thought about that much. And you can make use of that because it now means you have more energy spread in your electron beam. If you taper the undulator, you can get different parts of the undulator to laser at different energies with the same micro-bunches. And then you can recompress them back to make even shorter pulses. And he just points out, this is just natural. This is a great thing about free electron lasers. Everything happens for free. The machine cost $1 billion, but everything else happens for free. And that we'll be naturally making 200 attosecond pulses under a range of conditions in these machines. So the machine is going to be ready for us to do these things. Maybe. And we have to convince people that they should operate in the right way.
So this space charge is for the current operation?
Is it happening now? It probably is in cases where they are allowing the micro-bunching to evolve at the right rate. It
Because I
probably is.
thought that the density is not that high, right? And as you mentioned the other day, they're really heavy, these electrons.
Oh, that's right. But don't, okay, that's a really interesting thing that you just said. Yeah, they're really heavy. That means that it's very difficult to accelerate them or decelerate them. But it doesn't mean that it's very, the fact that they're heavy just means that they don't blow up.
Right.
But they still chirp their energy.
Yeah, but the space charge, I thought it's...
The space charge is the thing that's causing their energy to chirp, not their size to blow up.
Gotcha.
Right. The fact that they're stiff is great, because it means they'll stay micro-bunched even as they get chirped.
Okay.
Right? So, this is really a cool idea. That was wrong to genius. All right, I'm done. Strong field, laser fields can induce impulsive dynamics. Okay, go away from this talk thinking impulsive excitation. It's what we do in order to get science out of the experiments that we can match up to real calculations and make progress in this field. Tools now exist to extract spatial and temporal information about electronic motion, about nuclear motion in molecules on these timescales, and we're getting into this out-of-cycle regime. And X-ray FELs are going to have, I think, a really important role in this in the future. And I'm done. I've had a tremendous amount of fun here. You know, the weather was better the other time I came to this school, so maybe I had a little more fun then, but, you know, other than that, here's my group again. I showed them at the beginning, I'm showing at the end, because they are actually responsible for much of what, well, everything that we actually accomplish and a lot of what we think about. And that's the tip of the iceberg, because so many collaborations, of course all of the experimental groups are like this. Here are just a few alumni and collaborators. Okay. And finally, thanks very much for a wonderful week.
So remember, your last chance is for questions. Yes.
Assuming that you know the molecular structure beforehand, is there an upper limit to the complexity of molecules you can use this technique on?
No. That's a reasonable question, but I'm pretty sure the answer is no. And just to give you an example, it's not really in the impulse limit yet, but to give you an example of how things could go. People have used pump probe methods to detect the motion of retinol in bacteriorhodopsin. And that's a big molecule with a little tiny thing in it that's moving, and I still were able to do it. Now, you know, it's a special case in many ways, but nonetheless, it demonstrates this principle that even in highly complex systems, you can get really useful information. And I think the reason for that is because as long as you want to confine yourself to short time scales, you can simplify even these very complex problems. I mean, you know, the kind of problem you can't deal with in this way is something like protein folding. That's a big problem, very important problem. It's not a pump probe problem. It's something that just doesn't, there's just no way to get in there and do some kind of impulsive thing for protein folding. But for things like chemical reactions, you know, which are initiated, or catalysis, things that are initiated by getting over an activation barrier, and then everything happens. This is great. This is exactly the kind of problem you can solve.
For the free electron laser, and the spectrum would be a little bit random, so is it available to do the component control in the experiment?
Yeah, it's a really good question. In Girard's example, the bandwidth that he's seeing in this example at the very end, where he showed that you could make 200 attosecond pulses from the longitudinal space charge in the microbunch. That was something where the energy should actually be rather stable with respect to the center of the bandwidth of that pulse. And the reason for that is because that's a lot of bandwidth. In cases where you have longer and therefore narrower bandwidth femtosecond pulses, there's a lot of energy jitter that's much greater than the full width half max energy of a single pulse. And then you have problems with control that you have to deal with some other way. One of the ways that you couldn't deal with those problems even there is with external conditioning of the electron beam with a laser. I showed a little bit of that in my second lecture. I have one slide on it here too, where upstream you create an artificial density modulation in your electron beam that has a modulation wavelength that you chose. And you can actually control things better that way. Another way that it has been controlled at LCLS and is available for users now is through something called self-seeding. So Linda talked about self-seeding quite a lot, where you get a little lasing happening. You don't really know, it's got a lot of jitter and energy. But then send it through a monochromator, either a crystal or a real grading monochromator. Filter out the part that's at the energy you want and make that be the seed for the rest of the free electron laser. Then that works too.
On this attosecond pulse, does the dispersion or the dispersion compensation happen for free as well, or do you have to actively put these different energies back together in the light?
It's a second. Yeah, once it's in light, you can't play these games with magnet-based dispersion compensation. You have to use light-based dispersion compensation. Of course, we know how to do that. We knew how to do that first. It doesn't mean it's easy, but you'll have to worry about the second order phase separately from this. Now, I should point out that although I hesitate to call it impulsive, that stimulated Raman is independent of whether your beam is chirped or it's not chirped. Sort of an interesting thing. Well, it's not 100% true, actually. Depends on how far apart the Stokes and anti-Stokes line are. They could be so far apart that if you chirp the beam, you kind of lose it and it doesn't work. But generally speaking, because it only is concerned with pairs of photons, rather than the actual color of any one photon, some amount of chirp doesn't hurt you. It doesn't hurt you as fast as you might expect it would, just simply based on the full width half max getting bigger.
Other questions?
I have a stupid question.
I was going to ask one.
So I'm first. So I'm a two-state system guy, okay?
Yeah.
Sometimes I've done three, but it's kind of pushing my luck. Out of the gazillion of molecules which are available, how do you pick one rather than the other to do specific type of experiment?
Well, there's not one answer to that. If we're trying to do an experiment in the molecular frame, then we try hard to pick a very small molecule that we know how to impulsively align or at least get into some coherent motion. And then everything that we do will have to work for that, okay? If we're interested in making use of the range of soft X-ray wavelengths that are available at LCLS, see, this is really an important example of what you just said. There have been probably 100 experiments on LCLS on oxygen and nitrogen, and hardly any on sulfur. Why? Well, what colors can the laser produce? We say, oh, it's completely tunable from the carbon K edge at 300 eV all the way up to 12 kilovolts. It's completely tunable, but there are actually some regions where it almost pretty much can't get to because of the optics that are downstream. And 2 kilovolts, between 2 and 5 kilovolts is a really difficult region. And so it's a really important region for chemistry, by the way. So that really important region for chemistry is something that we just can't reach. And so we never do experiments that involve those kinds of atoms. LCLS2 will fill in the gap, which is very important.
So I have one question regarding this very beautiful experiment on the stimulated impulsive Raman. And so I'm only thinking in theory. I can also do it with the CW, 2-photon, 2-color CW lasers, and the matrix elements are the same. So what is the take-home message here? What is you gain in the yield of the photons? What?
Yeah, the take-home message is that what the high intensity buys you is that the rate of the 2-photon process will then become higher than the rate for the 1-photon process that forms your main background.
But
So-
compared to the CW Raman, the stimulated Raman.
But in CW stimulated Raman, you would not have a very high intensity.
That's right.
And therefore, the linear processes, like ionization, would be exactly the same as here, but the quadratic process, the stimulated Raman, would be much weaker. The cross-section is the same, but the fluence is down, or the intensity is down. It goes like the intensity squared. I mean, I think in terms of fluence, because I'm always interested in yield, right? But if you can think in terms of rate, so it's not fluence, it's intensity. And the fact that the intensity is down is going to mean that the linear process will not be adversely affected, but the quadratic process will. Yeah.
Very good. Any other questions? Remember, your last chance. Going once,
Okay.
going twice. Oh.
So where do you see the field in 10 years?
Oh, I think in 10 years we'll have a lot of attosecond sources in the free electron laser community. Fermi, Swissfeld, possibly even, by 10 years from now, possibly even in Sweden. And of course, we'll have Flash and LCLS2. And that's enough to drive a very robust community. And we'll certainly be able to explore this attosecond range, this charge migration problem. In fact, the charge migration problem there may be some new paradigm, as there was, for example, in BEC. When BEC first got started, we didn't even realize that it would actually shift the question of what's interesting science. So now you study different things, right? I think this has the capability of doing that as well.
Yeah, I think this charge transfer is hard not to crack. I think this would be very good. Yep, one more.
Do you have any reasons why don't you use seeding in LCS2?
Do I have any reason to do what with LCS?
I heard that you don't in LCS2.
Yeah.
You're not going to implement seeding process.
I'm not going to
Seeding.
we're not going to seed. Oh, I hope they do seed. It's, a lot of my campaign is to get that into the baseline of the project. There is some wiggle room in the baseline of the project right now. And they're not going to do HGHE seeding because that's too hard to get up to that. And that works at Fermi, but that won't work well if you're trying to get to, say, 3 kilovolts. But other things, these echo type schemes where you place modulations on the electron momentum by having it co-propagate with a laser beam. Those schemes will almost surely work. And my allies in this are all of the accelerator theorists, the FEL theorists, who just love this stuff. And I think together the AMO community and the FEL theory community will make sure that this happens at LCLS2. It's an ideal place. We've got the real estate. It hasn't been designated for any funding to do anything with, and this is what we're working on over the next few years. That's sort of a political impediment. It's not a physics problem.
If there are no other questions, then I suggest you join me in thanking Professor Bucksbaum for joining us. So we'll take a few minute break. We have time. And we will come back for the very, 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 very last lecture.